Hello, my little mathematicians. Today we're going to go through applying both the measures of center and then how it relates to variability. So let's go ahead and get started. For the top part, if you want to just go ahead and copy this down. Um, and you can always pause the video, of course, if I go too fast and you need to get more stuff. But for the most part, okay, symmetric versus skewed. Okay, so symmetric means that it looks symmetrical. So most commonly, it's like this, where it kind of almost looks like a hill, right? Okay, so your tallest point is the peak in the middle, and then it goes down evenly on both sides. That's perfectly symmetrical, but some of them are like kind of symmetrical if they're not exactly precise. Like down at the bottom, I would say that bottom graph in example one at the bottom is still considered symmetric, even though it isn't perfectly symmetrical like this dot plot up here. Um, and then other times it also like maybe it goes down in the middle, but then it like peaks up evenly. So that would still be considered symmetrical, like it's evenly balanced. Versus skewed means it like starts up on one side and goes down towards the other. Okay, and here it starts up and then goes down towards here. Those are both skewed. Now you are either skewed right or skewed left. And you're like, how do you know which one? Think of it as like the majority of the data is here, and then you have a few outliers that are skewing or messing up my data. Where those outliers lined, they're on the right side, so it's skewed right. Here's the majority of my data, and then I have a few outliers, and where are those outliers? On the left, so it's skewing my data to the left. So some people say it's where your outliers located, that's the direction it's skewed, or other people say like follow the hill down, and wherever the tail end of the hill is, wherever the tail is, that's the direction it's skewed. So whichever way makes more sense to you. I'm like, hey, the majority of the data is here, and then you have these few like screwballs messing up my data set. Where are the screwballs located? Oh, they're on the right, so it's skewed right. Here, the screwballs are located on the left, so it's skewed left. Whichever makes it easiest for you. Okay, so that's an example of like symmetric or skewed data. And of course, like you can do the same thing with like histograms and things like that as well. Okay, now there's measures of center. Of course, like there's mean, median, and mode, but we don't really use mode that much unless like the whole data set is the same number. The main measures of centers we focus on are mean and median. Okay, now the mean is the most common one that we use. And a lot of times, like graphs tend to be pretty symmetrical. And so if they're symmetrical, then the mean would be the one that you would use. And then the median is what you would use if you happen to have a graph that has outliers, like, one of these skewed graphs, because the outlier is really going to throw off your mean value. And versus if you find the median, like whatever's to the far right or to the far left that's messing up your data set, it'll get crossed off and then you'll get that middle value. So if there's outliers or your data skewed, then you want to use the median as your measure of center. Okay. And again, like it doesn't have to be like in the middle set of values. Like sometimes depending upon how it's located, like maybe it's here, which isn't exactly like in the middle. It's depending upon how your data set's set up. Okay. Now, in terms of what variability you want to use, if it's symmetrical, then you want to use the mean, and then like all the data is like pretty close together. So like the MAD value would be a good case to use for your measure of variability. You wouldn't want to use the range because it's way far off. And then same with here, like you literally have outliers, so you wouldn't want to use the range of the whole set for your variability. You'd probably want to use the IQR, which just takes the middle 50% into consideration, and then you cancel out those outliers. So what terms of variability you're using depends upon how your data set looks. And so like symmetrical graphs, those are good to do with histograms and dot plots. If the data is skewed, like maybe you want to do a box plot, and then you can see, because box plots divide it into 25% segments. So then you can see like a really long gap, like, oh, that data was really spread out and this data is really close together, and so on. So box plots are really helpful if your data is skewed. Hopefully I've allowed enough time for you to get all that down. If not, again, remember, you can always pause it and get it. Okay, now that we've rambled on enough about the different types and spreads of data and when to use what type of variability, let's go ahead and like analyze some of these graphs. So here we have Mrs. Mathiason's class, and the school nurse measured the height of each student in her class. So then she created a histogram to display the students' heights. Okay, so they ranged all the way from 40 to 64. Now, what sucks about a histogram is like, I don't know if anyone was actually 40. Maybe they're all 44. Maybe a few were 43 and 44. You can't tell exact specific heights, but you can at least like see the ranges in a histogram. Okay, but what would you say about the shape of this? Yeah, I would say it's symmetrical. Okay, I mean, it's not perfectly symmetrical like that dot plot we drew, but here's the center and then it goes down on either side. It's pretty much symmetrical. The best measure of center, if it's symmetrical, is what? Yeah, the mean value. Okay, and then because it's like fairly close together and this and that, then the best measure of variability would probably be your MAD value. Okay, you wouldn't want to do the extreme edges. It's like, how close is everything to the mean value? Javier says that the mean of the data will fall between 50 to 54. Do you agree or disagree with that? Yeah, since it's symmetrical, the majority of the data is going to fall in that large peak in the center. So yeah, I agree. Okay, let's go ahead and take a look at the next page. Okay, the next page, we have two different banks. Okay, it says 2 studies were conducted at these 2 banks, and the summary measures how long a customer had to wait in line. So at State Bank, they had a mean wait time of 8, and National Bank had the same mean time of 8. So you're like, oh, it doesn't really matter. Well, that's why it's helpful to consider the variability in the data set rather than only look at the mean. So here at State Bank, yeah, they had the same mean of 8 minutes. They have a MAD value of 6, whereas National Bank only had a MAD value of 1. What does that mean? So think of it this way, like on average, these are about 6 minutes away from the mean. So that means it ranges from 8 minus 6 to 8 plus 6. Well, 8 minus 6 is 2, and 8 plus 6 is 14. So this has a range of 2 to 14 minutes at this bank, right? Versus this average wait time away from the mean, 8 minus 1 and 8 plus 1. Well, 8 minus 1 is 7, and 8 plus 1 is 9. So this has a range of 7 to 9 minutes. I mean, it's not that far off, but at the same time, like this could be up to 15 minutes-ish, and this one, like the max is kind of about like 9-10 minutes. But this could be as low as 2 minutes, whereas the bottom here is like 7 minutes. So you're like, well, hey, do I risk it and like luck out that I get the 2-minute wait, or do I want to guarantee that I'm like 10 minutes or less? I mean, that's up to you, right? Technically, if you wanted consistency, you'd rather do this bank. But if you want to take a gamble and you're like, ooh, what if I look out and get the 2-minute wait line? Then you do State Bank. In most cases, like it's pretty obvious which one to do if you think of it that way. But for this one, it's kind of, it's a gamble. I would say I would like consistency, but some people would take the bet and do that one. And like, what if I luck out? I'm not willing to risk the 15 minutes, especially if it was a lot bigger of a wait time, like, up to like 30 minutes. It's not worth the 2-minute wait, is it? Okay. So again, that's just kind of things that you consider the MAD value. Remember, that shows you like the range it is from your average wait time. Okay. The next one says Citibank, a new bank in town, advertises that they have quick lines to satisfy busy customers. The data shown below compares the wait time for 10 different customers at both of those banks. Okay, so here are the wait times at National, and here are the 10 wait times at Citibank. So at National Bank, okay, let's find that mean value. So I'm going to add all these together. And divide by 10, right? So when I added all those, I get 80. And then 80 divided by 10 is 8. Okay, so National Bank has a mean of 8. Okay, now you're mad. All right, we got 5, 7, 8, 8, 8, 8, 8, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 9, 9, and 10. Okay, so from 8, how far away are each of these times? Well, that's 3 away, 1, 0, 0, 0, 0, 0, 1 away, 2 away. So if I add all those numbers, 4, 5, 6, 7, 8, and divide it by 10, that has a MAD of 0.8. Okay, let's compare that to Citibank. Okay, for Citibank, if I added all these together, type that into your calculator, and then divide it by 10, you should have gotten a total of 60, and divide that by 10, you get a mean of 6. Okay, so their mean is 6. So then to find their MAD, 3, 3, 5, 1, 2, 3, 4. Okay, 1, 2, 3, 4 fives, 7, 8, 9, 10. So let's see how much their variability is by checking out their MAD. Okay, so when I look at Citibank's MAD value, from 6, 3 is 3 away, 3 is still 3 away, 1, 1, 1, 1 away, 7 and 6 are 1 away, that's 2, 3, and 4. Add all those together, 6, 7, 8, 9, 10, 11, and then 13. 13 is 16, so we get 20 total divided by 10, and that is 2. So you have a MAD value of 2 and a MAD value of 0.8. Okay, they have this line, so we probably want to draw a dot plot. So from here, it goes all the way from, what's your smallest value? Your smallest value is 5, and your biggest value is 10. So I'd count by ones. Here's from 3 to 10, so I'd count by ones again. Let me go ahead and just put that right here. Okay, so this kind of shows you, like, how it's spread out. Are either of them, would you say, symmetrical? This is like maybe symmetrical-ish within like an outlier there. This one, not really. It's kind of all over the place, right? But I'd say maybe like skewed to the right, but not really that skewed because they're all right apart. Okay. They're pretty close together. However, look at the MAD values. This has more consistency, right? Like they're closer to 8 versus this could go as low as 4 and as high as 8. So this one on average typically has like you'd be a better wait time there. Okay. All right. Let's go ahead and answer some of these questions. It says calculate the mean number of minutes in line. Okay, which we did. Does Citibank live up to their advertisements? What do you say? Yes or no? Okay, so the mean for National Bank we found was 8. Okay, while the mean for Citibank we said was 6. So on average, Citibank customers wait 2 minutes less than National Bank. So like, did they live up to the hype? Yeah, Citibank on average waits less. Okay, the next one says, if you wanted a consistent wait time, then which bank should you use? Okay, I kind of already answered that. What do you think? How do I know which one's more consistent? Yeah, you look at the MAD value. So the National Bank is more consistent because it has a MAD value of 0.8. Okay, and then Citibank varies greatly with a MAD of 2, and it has a total range of 7 minutes. You're like, what is that? The total range is the top minus the bottom. So like 10 minus 3 is 7, and here 10 minus 5 is only 5. So they have a smaller range and a really small MAD value. They have a big range and a really big MAD value. So if you want consistency, you'd go here, but like this one, it's like you kind of on average they have a less wait time, so you might want to like gamble that one, but consistency, then you'd want that one. All right, and that's how you kind of take variability into consideration. Hopefully you understand variability and like the measures of center and which one to use a little bit better after today's lesson.